So far we've looked at the atom in terms of what the electrons were doing. And so the atom evolved through those different models as physicists attempted to describe the behavior of the electron. Now, it got to a point where physicists wanted to determine were the proton, neutron, and electron the smallest bits that actually made up matter. Now, spoiler alert, they're not. You see in this diagram here that there are neutrons and protons in the nucleus, but they're actually made up of something called quarks. You might have read about quarks in the news. If you've kind of watched stuff that has to do with the Standard Model, they would have been talking about quarks. Now, these quarks are interesting because if you take these now and put them in different arrangements, you get all these different types of subatomic particles with different charge, different masses that scientists started to actually observe. Now, what we're going to focus on in this video is the detection devices that early scientists use to actually see these subatomic particles. Now, one of these detection devices is what's called a cloud chamber. And it really is just that. It's a chamber that contains a cloud. It was designed by a Scottish scientist who was trying to study these weird shadow phenomenon going up at very high altitudes. And now in order to do that, he built this chamber where at the top is kind of this felt solution. So at the top there is a felt solution. And then at the bottom is a very cold piece of metal. Underneath that is dry ice. That felt solution at the top is saturated with alcohol. You can see it dripping down in the video there. Now as it drips, it kind of goes through this temperature gradient and it starts to cool down. And as it gets to this bottom part of the cloud chamber, it starts to condense into a cloud. Now what the guy who designed this saw is that all of a sudden there's these little tracks being left in this chamber. And so it was the very first time that we started to observe these subatomic particles. And the way it works is that these droplets are on the verge of condensing. And any little disturbance is going to cause them to condense into liquid right away. So you end up with charged particles whizzing around that were previously invisible, but they whiz through this chamber and then they leave behind these streams, much like jet streams when you see an airplane passing high in the atmosphere. And then you shine a light through and you can actually see these trails a little bit better. In this video, you'll see the droplets fall from the ceiling of the cloud chamber, and as they fall, you can see that they condense. But watching this video, if you see these streaks in those droplets as they fall down, those are subatomic particles. And based on the characteristics of these different streaks that we observe, we can identify these particles. And so it opened a whole nother realm of atomic physics as soon as physicists started observing these particles with different masses, different charges, etc. Now in this video, you'll see some that travel very straight. Those are most likely muons. You'll see kind of zigzaggy tracks. Those are probably electrons. And then anything that's a little thicker is potentially alpha, kind of like in this diagram there. But that's just a very easy to build device that you can build in the classroom. And it was one of the very first particle detectors that we had. Another way is kind of to go the opposite way, and you take a liquefied gas and you build what's called a bubble chamber. So as the particles come through here, they actually leave behind bubbles. They cause this liquid to actually boil because it's at such a low pressure. And then it leaves behind bubbles, and again you get these images. You get images like this one where there's all these different paths with different radiuses, etc. And from that we can actually identify what particles are there. Because you'll notice in this diagram there's these magnetic coils on the outside, which we usually use to operate a cloud chamber or a bubble chamber, because we know that charged particles are actually going to bend in a magnetic field. So based off of that and a couple of simple physics principles, we can identify what these particles are, because we know that positive and negative particles are going to curve in opposite directions. That's our third hand rule. Lighter particles tend to curve more than heavier particles. Heavier particles have more momentum, and so it's going to be a lot harder to kind of change their direction. All conservation laws must be obeyed. That's important. if we have a neutral particle that all of a sudden hits something and splits, we can't form only a positive particle. We need charge to be conserved as well as momentum. And neutral particles don't leave tracks. So we can look at this diagram. It tells us that one of these particles is an electron and one is a proton. From that, we can probably identify right away that A is an electron. The reason why it's an electron is because it's curving a lot more. So it's probably a smaller particle. But we can use our left-hand rule to kind of look at that. Here's my left hand. Here's the direction that the electron's initially going, and then that magnetic field is making it travel in a tighter and tighter circle. You're going to have to imagine the fingers here coming out of the page, because we know that that palm is the centripetal force, which is the magnetic force that's kind of pushing it into that tight circle. So from that, just in the diagram in A, we can determine that that magnetic field is coming out of the page here. And then using that, we can actually use our right hand rule. So here's my right hand. To determine that B, so it's coming out of the page. If I take my right hand here for B, that magnetic field is coming out of the page. Where's the right hand? This is the right hand. Coming out of the page. These hands are kind of all messed up in their directions. But we have this proton here. If it's traveling in this direction, my fingers are coming out of the page, and then that magnetic force, again, is towards the center. It's traveling in a bigger radius because it has more momentum. So we can use our hand rules that we took in from forces and fields, along with our physics principles, to identify what these particles are. And typically in these kind of types of scenarios, we have a diagram like this that's been collected from a bubble chamber or a particle chamber. There's another interesting diagram here, which was collected from one of these detection devices. And the implications of this one is actually pretty interesting. We had a neutral particle before, or something neutral, probably something like a photon, which wasn't detected. You'll see kind of in this diagram, there's nothing going on here. So it wasn't leaving behind tracks, so it must have been neutral. And then all of a sudden, it split. And we ended up with two circles. Now the interesting thing is, if you look at both of those circles, their charge to mass ratio is the same in magnitude, but they're in different directions. So say if this one's an electron, this one has the same charge magnitude and the same mass as an electron, but it has a positive charge. And that's actually what we call a positron. It's an anti-electron, and this was actually one of the first instances of antimatter being detected. And so we can take something neutral and it can split apart and form this matter-antimatter pair. And just the same way, we can have an electron and a positron that we see in these diagrams, and then all of a sudden they disappear because they annihilate each other. And then that mass is converted to energy. But you can see in this diagram antimatter. And so these very early on detection devices allowed us to actually start to talk about a lot of very sophisticated physics, like antimatter, etc., just based on these very simple chambers that allowed us to see this stuff that was going on all around us.